So we've been motivating a framework that emphasizes describing our statistical inferences by quantifying uncertainty, right? This is in contrast to a null hypothesis significance testing framework that was laid out by Timo yesterday and mentioned briefly today as well. So we're now going to turn our attention to making statistical inferences under a Bayesian framework. Now, currently there are tons of methods to choose from, and I'm just going to describe what we believe to be some of those that are the most common, right? So this overview will not be exhaustive. It can be quite frustrating because you learn something new and then a week goes by and someone's doing something different. That's the method you learned before is no longer valid or whatever. Sometimes it's hard to remember that statistics is its own field and it's developing on its own. So we'll keep that in mind, and we're going to talk about 3 methods that seem to be rather constant. You can think of these methods as new tools that we're going to be putting into our toolbox for how we can draw inferences and examine the models that we are fitting. I don't believe that any single tool that I'm going to talk about is better than the others, but some of them might be more appropriate for the types of questions that we are interested in answering. So the first thing that I'm going to talk about is the credible interval, and we've actually already heard this word thrown around a good deal. We're going to get a little bit more detail about it. If you've heard of Bayesian statistics before, Bayesian inference before, there's a good chance that you've already heard of credible intervals. We could describe them as being the counterpart to confidence intervals under a frequentist framework. Some might say that the difference is merely philosophical. I won't go into that too much right now, but if you are interested, I would suggest maybe Google searching or searching on Twitter something about confidence intervals, and you'll see huge fights and people that are in statistics Twitter. I will give a definition of what one I got from a textbook for what a confidence interval is, which is the long-term relative frequency of the estimator containing the estimand in an infinite sequence of replicated experiments under ideal conditions. That is not very intuitive to me. I find that to be quite difficult to understand. The important thing here is that most of the time, what people think a confidence interval represents is in reality what a credible interval is. That is the interval within which an observed parameter, a parameter estimate, falls with a particular probability. So when we describe a posterior distribution, we typically say that a specified % of the posterior falls within a certain range. So in this plot that we see here, I'm using color to highlight part of the posterior that falls within a certain range, right? So the purple part, for example, is falling within a specified range. To give a more concrete example, you might hear somebody say something like the probability that beta or any given value is between 10 and 20 is 0.95. Or you might hear it said another way, like we're 95% certain that the value is between 10 and 20, right? This is how we can use credible intervals. This is an informative way to quantify uncertainty when describing a posterior distribution. These types of interpretations that I just gave are not available to us with confidence intervals under a frequentist framework. So in the case of the plot that you see here, we're 95% certain that the value of beta falls between 10 and 20. As I alluded to before, you don't get the same interpretation under a frequentist framework. I'm underscoring that again just to make sure that's clear. So some researchers use a 95% credible interval to make statistical inferences by saying something like, if the 95% credible interval of the posterior distribution of any given parameter does not include 0, then we'll consider that to be compelling evidence for any given effect. That's one method. And that would certainly be the case in the plot that we see here. As we can tell, the entire posterior distribution falls pretty far away from 0. But obviously, that's not always the case. For example, a lot of times in my research, it seems to be the case anyway, I find something like this, right? Where we've got some of it is encompassing 0, but not all of it. It overlaps by a pretty large amount in this case. So for some researchers, we would conclude that there is not compelling evidence for a particular effect, that this would be evidence that is inconclusive. Now notice that I've used 95% in the range here and in the previous examples, and pretty much everything that we've talked about so far over the last 2 days has been 95% credible intervals or standard deviations covering 95% of a certain range. This is without a doubt the most common range, most common value for that. And it is a carryover from the null hypothesis statistic testing framework. We use p less than 0.05, for example. It is completely arbitrary when we think about credible intervals. You can use any interval you want to describe a posterior. 95% is just the most common. It's become a standard. But the important thing is, no matter what the interval is, you're describing the distribution, right, in terms of its width. So now we're going to practice with a couple examples. It says live coding, but that's a bit of a lie. This is going to be guided coding, I guess you could say. What I'm going to do is I'm going to bring up one of the exercises that already has all of the examples I want to show you programmed into it. So this way, you have three options with how you can do this. You can follow along with what I'm doing and just kind of sit back and relax. You could also look at the website right here, which I'll post into the chat, which is just, let me move that so I can grab the link. This is just the same R Markdown document that I'm working from, but it's already been knitted. So let me get back over here. I'll put this in the chat. There you go. So you can just look at that. I'm basically going to give the same information. Or if you want to, you can also, excuse me, you can also open up the exercise that I'm looking at using this function right here. And you can actually knit the document as I go along and do it too. So whatever you prefer is fine. Now, when I do coding, I do get a little bit excited. And I'm going to try to calm my emotions and not go too fast. But obviously, if I do, just holler at me and tell me to slow down. So the stuff at the top here, we can just go ahead and ignore, but this is just showing us that this is an R Markdown document that will produce the website that I pasted in the link. If you are in a new session, then you'll want to load these packages. But if you did this before with Timo and it's the same session, it won't be necessary, but I haven't loaded them yet. So I'm gonna go ahead and load all these packages. There is one that's new here that I do want to highlight that I don't think we've used yet in anything we've done so far, and that is the Bayes test R package. Now, with your installation of the Learn for, oh, larger font, thank you. That's probably too large. Is that okay? It's not. Great, awesome. With your installation of the learnB4SS package, you should have had this one installed as well, but if not, you can just run library Bayes test R. And if you, for whatever reason, you don't have it, then you could use the packages tab and you could just install it. It's on CRAN, so it's widely available. We're going to find that this package has some very useful functions that are going to help us with doing statistical inferences, and it also has plotting methods. Let me go ahead and load the data here. You can ignore this. This is for making the plots look pretty, but it's not important to what we're doing. So the first example I'm going to talk about with using credible intervals, I'm going to just create a fake posterior distribution. So without running any model yet. And I'm going to grab values that are they're theoretically distributed as normal. They're coming from a normal distribution. I'm going to say, just give me 1,000 with a mean of 5 and a standard deviation of 3. Now, when I run this function, it's just going to give me a vector, right? It's just a vector value. So I'll run this and show you. And it's going to just be 1,000 numbers, as you see in the console. Now, the reason why I'm showing you this with just a vector is to explain to you that the tools that we're going to use here work on different types of objects, right? The most basic one being just a vector. And I can use standard functions in base R to summarize this distribution. For example, we did this earlier. I can get the quantile of the posterior, and then I could say, all right, let me know the quantile at 2.5%. And also at 97.5%. I use these values because this is what would give us a credible interval, for example, with a posterior distribution. So if I run this, let me make this go away, we can see that we have a range from negative 0.769 to about 10.99. If you run this exact code, your value will probably be slightly different because I did not set a seed, so it's randomly generated numbers. Okay, awesome. Now, what we're going to do is use a function from the Bayes test R package called HDI. HDI is a certain type of credible interval, right? There are different types of credible intervals. This one, the characteristic that defines it is that all of the probability mass that is inside the interval that you specify is greater than what's left outside of it. It's particularly good when you have a distribution that might be slightly skewed in some way. So I'm just going to run this code and then open the object, and we can see it gives me an HDI that's actually slightly different from what I calculated with the quantile function, but it's within the same range. Again, it's calculating the credible interval in a slightly different way. Awesome. So this is pretty easy. The HDI function is quite handy, and it will do this for us on any type of vector of values. What's really cool about it is that it also has methods in the package for plotting. So I can actually just take that object and put it into a function called plot, send that to the console, and I automatically have a nice plot that looks pretty good, and it will explain to us the credible interval, right? The highest density interval in this case. Whatever we see in red is within the default range of 95, and then what we see in blue is outside of that range. So this is a nice, easy way that's quick and dirty that will give us a plot so that we can visualize a credible interval. Now, that's great, that's wonderful, but obviously we're doing this typically by fitting models. Okay, this model was already saved, so I don't have to fit it again, but this was a model that we did yesterday. This was just the intercept only model with articulation rate. You can run this and you'll see values that we looked at yesterday. This should all look familiar. We have an estimate of 6.68 syllables per second. And then we have the estimate of the credible interval right here of 6.52 to 6.83. So what we're going to do essentially is get this same value, but now we're doing it on a model object as opposed to doing it on a vector. So we're kind of increasing the complexity of what we're operating with here. I'm going to skip down to line 115 if you're following along. And I'm going to use the function that we also saw yesterday to grab samples from the posterior distribution of our model. So I put the name of the model object right here, and I run posterior samples, and then I'm storing this as another object that I'm calling post 0, 0. So it's a posterior distribution. And again, I could send this to the console, and we can see it's 4,000 values, plausible values for the intercept and for sigma in this case. Now, I can do the exact same thing I did before. I'm going to take this posterior distribution, and I'm going to use the $ notation here to pull out one specific column. So it's basically just going to give me a vector. In this case, I could actually send just this to the console, and what you'll see is a vector of 4,000 values. And I'm going to send this to the HDI function. And this, you're going to see that it does the same thing that we did before when we created a fake posterior. So I'll run that object, and we can see this value right here, 6.52 ranging to 6.83, is exactly what we saw when we ran just the model. Got that right here, which is this value right here, right? The credible interval for the intercept. Awesome. Just like before, we can use the plot methods from this function to get a nice plot of this posterior. And in this case, we see that the intercept is much further away from 0, right? Way out here was 6.48 or 6.58 around there. And we can, for some researchers, this would be compelling evidence, for example, of this effect, that the intercept is different from 0, because we can say this seems like a reasonable margin, far away enough from 0, it doesn't encompass that at all. So that's one way that we would provide evidence for a given effect. Now, let's do this with a more complicated model. For example, you could run the one that you see here. This was also one that we did yesterday, so you might have it saved, but if you don't, you can just call this code right here and run it again. I have it saved. Actually, you know what? Scratch that. If you go to line 158, I think you can run it automatically because I believe this is already saved in the package. So you don't have to run the model if you don't want to, but feel free to. Let me just double check that. Yes, so here's the model we ran before. I'll make this a bit wider so that we can see the entire summary. There we go. And again, I'll call your attention to these two lines right here of the population level effects. Now we have a reference level that was impolite, that's our intercept. And then we have the polite condition, right? We see the difference. This is the same values from the model that you just live coded with Timo. Now, we can use our posterior samples function on the model object, and that will give us a posterior distribution. So I can run that, take a look. And there's our posterior, 4,000 values again. And I can use this, the same way I did before, I could use the $ notation and pull out a column from the posterior if I want to. Send that. Same thing as before. Here's the posterior for the intercept in this new model. ranging from negative 0.71 to 0.13. And if I want to, I can stick this into a plot method, just like before, and I see the same thing, right? In this case, we see that the 95% credible interval, again, does not encompass 0, though some of the posterior density is in that range. But for some researchers, depending on what your criteria is, this could be compelling evidence for an effect as well. And I want to show you that while I've been pulling out the posterior distribution specifically, we can also run it directly on the model object if we want to. So this was the model object that gave us the posterior. This is a shortcut, but I just wanted to show you all the possibilities. And what this will do by default is give us a markdown formatted table, which is also quite nice for if you want to post this in our markdown document or whatever. And we can see we have the intercept, the HDI, and then the reference or the second level of attitude, polite condition, and the HDI for that as well. And just like before, we could store that as an object and put it in a print method. And now we're plotting the entire model. Quite useful. The idea here was to start from something very simple and then piece by piece add complexity to it. In most cases, you would probably just jump to this last step, but any of those are fine. And this is a good forest plot for understanding our model based around a 95% credible interval.
Joseph, can you, this plot is fantastic. I think it would be really worth briefly talking people through what you see here and how this is to be interpreted. And maybe you can link that to what I just showed in the live coding. I mean, this is not intuitive for everyone. It's maybe worth reminding. Yeah, that is a good point. And that's actually something that reviewers say to me a lot because I like posting forest plots instead of other things. So this is essentially taking like the model output in table form like this, right? It's like taking these two lines right here and then making it into a plot, right? We see both of the parameters that we've estimated, the intercept and the attitude pull condition, right? And it's telling us the estimate, which is more or less where this is based around, where it's centered around, and it's giving us the entire posterior distribution with the interval. So this is the entire posterior, and it's saying which part of that contains 95% of the probability density. Okay, so when we look at this, as I was mentioning before, for some researchers, one way of saying, how do I tell if there's an effect or not? Like, where's my evidence? How do I make a decision? You would look at this, and if your criteria is having an effect that is a reasonable distance away from 0, right, like a point null of 0, for example, then this is one where we would say clearly the intercept is not 0. It's non-zero. It is definitely reasonably far enough away. We have compelling evidence for an effect. And if we want to know what's going on with the attitude condition, this is one of those borderline cases where you could say, okay, if my criteria is 95% of the HDI not encompassing 0, then we can say, okay, there's compelling evidence for an effect here. But as I said, what this indicates with the slight overlap with blue is that there are possible plausible values given our assumptions and the data that we have that the effect for attitude could be positive, right? Because it's right around 0 and some of them are on the other side of 0, right? I don't recall specifically what you wanted me to compare this to with your live coding. No, that's perfectly fine. Okay, that was maybe there's a time to squeeze in one question that is really important and relevant, maybe. Yeah. Chris asked, isn't that, so basically the way you presented it, some researchers might use the threshold here to make a decision whether something is compelling evidence or not, right? Yes. And that is, again, a threshold-based decision procedure. If 0 doesn't fall within this interval, then we call it compelling evidence. Right. That is exactly right. And that is, I would say that there are different opinions about that. And I think that the three of us are in agreement that we try to avoid that. But there are people that are proponents of Bayesian statistics that do it in this way. For example, some of the papers by Kruska focus on that, on decision making. And sometimes in some fields, you do have to make decisions. So that is one way that it could be used. Well, I don't necessarily think that's how, I don't want to say that's how people should use it, not because whatever, people do what they want to do. That's not how I use it, because I believe that you get more out of it by giving a description of what the posterior tells you and quantifying the evidence, quantifying the uncertainty around it. But it is true to some point, there's kind of no way around that. What is an alternative to using 0 for decision making? Fantastic. That is what we're going to talk about next, coming up in just a second. Is there anything else that either of you would like to throw in there before I move on to probability of direction? All good. Go ahead.
Sounds good. Okay. So then I'm going to leave this here for now, but we will be coming right back to it. Let me get my screen synced up again. Okay. So that was one method. That's one tool that we just put into our toolkit. I don't know, it's people have done it. Timo has papers published that uses that method, for example. Here's another one called the probability of direction, right? Oh, there we go. It's also known as the maximum probability of effect. It can range, it's going to give us values that can range from about 50% to 100, or in probability, 0.5 to 1.0. And it has actually a quite intuitive interpretation, even though this definition I'm going to give you might not work that way. It says it's the proportion of the posterior distribution that has the same sign, that is, if it's positive or negative, as the median of the distribution. If you think about it a minute, that makes sense, but you can say it another way. It's basically, it tells us the probability that a given parameter estimate is positive or negative, which is actually pretty, if you think about it, pretty useful information to have. So to illustrate, if you have a probability of direction of 100%, the interpretation is that you are 100% certain that a given parameter is positive, right? Or negative, depending on which way the sign goes. On the other hand, if you obtain a probability of direction of 50%, then the parameter is equally likely to be positive as it is to be negative. And that is quite a bit of uncertainty. Basically, you could flip a coin, you said you don't know if there's any effect at all. Right, so that's kind of the range of values that we're working with, and the types of interpretations that are available to us with a probability of direction. This is probably the closest equivalent to a p-value, but I'm not going to talk about that too much. But people use this and people refer to it in that way. So that's a kind of a warning, I guess you could say. It's actually quite simple to calculate, so I don't need more slides on this. I'm just going to go right back to our studio, and we'll look at some examples of probability of direction. So now I am down to around line 226. There is a function from the Bayes test R package that is called p_direction. I'm going to run this on the fake posterior that we generated before. I'll send this to the console. Try again. I will send this to the console, and it tells us directly the probability of direction is 0.95. So with this posterior, again, it was just 4,000 random values that I created. It's telling us there's a 95% chance that the mean of this distribution is positive. Okay, it's a pretty straightforward interpretation. I can do the same thing on the posterior distribution that I fit before from our intercept only model. So I'm just going to take another vector, right, using the dollar notation of just the 4,000 values that were plausible values for the intercept. And I'm going to send this to the same function, send it to the console. And in this case, the probability of direction is 1. So we're 100% certain in this case that the effect is positive. All of the posterior distribution is on the other side of 0. And if you recall, that's this plot right here where it's around 6. So it's really far away. I can use the same thing directly on the model. I'll do this in this case on the model that had polite, and we can see that it gives us an output in table format, and it includes all of the parameters that are estimated from the model. So that's actually quite useful as well. We can see them both, and they're both quite close to 100%. So we're pretty certain that these effects are in the case of attitude poll, we're pretty certain that it's negative, and the other one we're pretty certain that it's positive. And again, just like the other functions, these functions have print methods or plotting methods. So I can save it as an object, and then I can send it to plot, and it'll make a plot for me. In this case, you have to set the argument show intercept to true so that you can see all of the intercept as well. If I change this to false, it will get rid of that, and it'll plot just the attitude poll, right? But what we see in red, right, is the effect of the direction. So all of this in red is negative, and then in positive, which would be on the other side of 0, it is blue. And in this case, that would be the 0.30 that's left over here. That's in blue. So, right, the probability of it being negative is very, very small. So this kind of supports the tentative conclusion that I mentioned in the previous example with just using the credible interval, where I said, there looks like there is some small area of the posterior distribution that was on the other side of 0. Awesome. So I left this in here, but I'm going to skip this because it has to do with p-values, and I'm actually not going to talk about that. I'm just going to leave it at that for right there, because this one is quite simple. Let's see if I'll take a couple more questions here. if there's any.
Yeah, I have a juicy one for you. I'd love to hear your opinion.
Juice.
What does your conclusion look like if you don't use a decision threshold?
Right. That's where more adjectives come into place. I think the way that I typically describe this, and this is actually something I learned from Timo's papers, is saying giving the information from the parameter estimate and saying that specifically that like this, we find this to be compelling evidence for this effect because it is a reasonable distance from a point null, for example, if you're using that framework. That isn't specifically what I do right now, and I'm actually going to get to that as we go along. But that is one way that people do it, and I think that that's pretty standard. It's pretty accepted now. Where you might get pushback specifically from reviewers is from people that don't understand what some of these new things mean. For example, if you talk about a probability of direction and the reviewer has never heard of that, that's where you have to give more information about what that means. But I do, in my experience, I do find that is becoming less common, at least in the journals where I typically publish. Your mileage will probably vary with that because obviously people are more or less familiar with Bayesian statistics in certain areas.
Yeah, let me jump in there real quick. So you're quoting me, quoting me. Basically what I did when I started with Bayesian inference is I sneaked the decision procedure through the back door. That is, I used a quantitative construct that Joseph just introduced, and I defined a threshold that I subjectively consider compelling evidence or not. That's very similar to what we do in null hypothesis significance testing. And as you now probably look at me in a puzzled way, because I kind of emphasize that we want to avoid decision procedures altogether. So I guess the question, and this is really a tough one, so what do you do? So the big reason, practical reason why I did that in my papers was that it was very difficult to describe the results in a way that reviewers were satisfied. Right? So if you can't make a black or white decision, how do you know that something is meaningful? How do you know that it's worth talking about? How do you know it's worth hypothesizing about and speculating about its theoretical impact? An alternative to any kind of decision procedure is to describe this posterior distribution, and that is it. You can obviously relate it to certain thresholds, right? For example, 0, because we're used to comparing to 0, but Joseph is in a second going to talk about a very particular way to relate these values to. But it's literally, you relate the most plausible values to your world knowledge and your knowledge about the underlying system. And you do not make strong black or white decisions as to whether there is a certain quality to this evidence over another. That would be the way. That sounds probably very unsatisfying and challenging to publish, and it truly is, unless the field changes in its entirely. But that would be the way. You describe the posterior, and you might relate it to other values. But a very important kind of way to describe results in the Bayesian way that's not done in null hypothesis significance testing is a little fragment of a sentence that we add to our statements. And that is, given the model, the data, and our prior assumptions. So whatever we claim is usually qualified by reference to this goes for this model, for the data that we have, and for the priors that we specify, right? So it's kind of already a more humble way of stating it. And I have to also say something here. These posterior distributions, and we touched on that, they are dependent, very much so, on your model architecture. Right? If you do not specify an appropriate model, for example, you're not taking into account random effects. When you have a data set that just justifies such a grouping factor, you will be anti-conservative. You will underestimate variance, and your posterior will be narrower than it should actually be. Meaning, based on your model, your prior assumption, and your data, you will potentially make the wrong decisions or even the wrong description of the plausible values that you see. Right? So that can all go wrong in Bayesian world as well. That's just a couple of clarifications from my side.
Yeah, no, that's great. And that's exactly it. It is, or it feels rather unsatisfying at first, because you get stuck in some of those positions like, well, how do you know? Or how do I say this? How do I sell this to somebody else? And it's something, I guess, as the field grows, we will get better at this, I think, and just describing our uncertainty is much better than trying to just say make a black or white decision. Let me get back here, and we will see that what Timo mentioned is based on the data and our prior assumptions about the data. That's something that's going to come up a lot more as we talk more about this. And this third and final method that I'm going to show you in some way combines the credible interval with something else that's called a rope. And I find this one to be more satisfying, and it has some other options, I guess, for interpretation that we will talk about. So we're going to combine our highest density credible interval, or just a credible interval, with what's called a region of practical equivalence, or a rope for short. Now, the idea behind the rope is that it's probably rather pointless in many cases to test whether an effect is exactly equivalent to zero, right? It's fairly rare that an effect is exactly zero. And if you have enough power, you can always find a significant effect, right, under an HST framework. So a rope allows the researcher to define a range of values which they consider to be practically equivalent to a null effect. To give an example, you could think of like reaction time, a study that uses reaction time, and maybe you see a difference of 0.5 milliseconds, and you just have tons and tons of participants, so it comes out as significant with a nice little star and a low p-value. Most researchers would say, well, what does 0.5 milliseconds mean? Is it something that's actually meaningful, or cognitively, or whatever framework you're working with? So in other words, in many cases, we establish this region around the point null of zero, but it doesn't have to be there, right? The rope represents the proportion of the credible interval, or the HDI in this case, of a posterior distribution that lies within this region of practical equivalence that we can establish. And I've noted a few studies here where this is detailed quite well, that are there for reference if they're more interested in reading about ropes. Let's look at an illustration. So for example, consider this plot that illustrates a region of practical equivalence in gray around a point null of zero. So in this case, I established a rope of plus or minus 0.01, okay? And we're gonna fit a model, and we wanna see how much of this 95% credible interval overlaps with our rope. So what we're gonna look at is the percentage of the posterior, specifically the percentage of the credible interval that falls within the rope. So we can put here, for example, a distribution. Here we can see that the posterior mean is 0.3, and the credible interval ranges from 0.16 to 0.77. Furthermore, we can see that about 15.67% of our credible interval falls within this rope. I say we can see that specifically, I put it right here so you can read it, right? This is visible in the plot with the orange vertical slab, where typically it should be purple-ish, but if it's inside of the rope, we show that with a different color, right? So just to reiterate, we're looking at the percentage of our credible interval. You see the interval right down here at the very bottom, the percentage of that falls within a region of practical equivalence that we have established, okay? Now, if the posterior falls further from the rope, as is the case here, I just changed the plot, it follows that the percentage of the credible interval that falls within the rope also decreases. So we're moving further to the right with the distribution, and we see that the value right here for the percentage within the rope is also lower, all right? And then obviously the mean increased as the credible interval changed, right? We could also consider an credible interval that is completely outside of our rope. So in this case, we see that the percentage inside the rope is 0, right? And this is something that we could consider as compelling evidence for a given effect. What we've done essentially is combine what we used before in the credible interval, right? And we're giving ourselves more tools to describe the posterior distribution. And at the end of the day, description is kind of the key here, what we want to do. So at this point, it's important to say that the researcher is responsible for determining the range of the rope. Right here, I use plus or minus 0.1, right? You also have to establish what the width of your credible interval is, right? We use 0.95 by default because that's kind of a standard, but it could be anything. It's up to us. So you might be asking yourselves, how does one go about doing that? How do we decide how to establish our rope and how wide it should be, right? In many cases, we have domain expertise regarding what a meaningful effect size might be. For example, if you're a researcher that works with reaction times, you know if 5 milliseconds is important to your research or not. But we can also relate this to previous research. That's probably the most common way if this is something that's new in your field, right? It's also possible to collect pilot data and base your rope around samples of data that you've already collected. You could also do this in conjunction with a power analysis. We mentioned this yesterday. This is actually quite difficult because there's a lot of moving parts there, but some people do this. And there are also some rules of thumb that exist. For example, if you're using standardized variables, for example, they say that a plus or minus 0.01 is quite good because it essentially is half of what Cohen's d considers a small effect. Now, that also brings other problems because what a small effect is using Cohen's d, for example, it can also be field specific. So these are rules of thumb. Rules of thumb don't always work, but these are consideration and these are things that people are doing right now, for example. There's also, if you do A/B type research, A/B testing, there's also formulas like the one given here from Kushka in 2018 that give a way of estimating what your rope should be. My experience playing with all of these methods, that it almost always ends up being quite close to plus or minus 0.01, but it does depend on what you're looking at if you standardize your variables. So the takeaway here is that one of the overarching themes of this workshop, what we've been talking about yesterday and today, is that this requires thinking and planning on the part of the researcher, right? All of the decisions that you make, it might seem arbitrary. Well, what is compelling evidence? That's true, but it's also has to be justified, right? As Timo said before, it's not just based on the data and the model, it's based on our prior assumptions about these things. And it's baked into the model. And we have to be upfront about that. We have to talk about that when we publish, for example, and people say, okay, given your assumptions, does this seem like reasonable evidence for whatever you're studying? So let's try this again in R. Let me see back over here. I haven't looked at the chat for a while. Sorry if I missed something important. All right, so now I am down to about line 315. And I'm going to do the same process as I did before. I'm going to work with our fake posterior. It's just the vector values that I created. We're going to use the function called rope. Rope function it does exactly what you would think it does. It's going to calculate the percentage of the credible interval that falls within a rope. Now you might be saying, okay, what is the rope and what is the credible interval? By default, the credible interval is 0.095 and the rope is actually calculated automatically. And I'm going to show you a little bit more about that in just 1 second. We could also manually specify what we want the range of the rope to be. There's an argument inside the rope function that's called range, right? In this case, I specified it to be -0.1 and 0.1. And I specified the credible interval to be 99. So this is a more conservative approach, you could say. Now look at this, and it tells me directly in Markdown that 0.91% of the credible interval falls within the rope. So if you are looking for a given effect, then you would expect or you would hope that this value was smaller, right? The higher the percentage here, the less likely, the less evidence you have for a given effect. This is just the formula. So as I mentioned before, there is a function called rope range that will actually calculate a rope for us. And you can just put in a model object. So this is the same model object that we were using before. I'm going to run this into rope range, and it'll give us a rope range based on our outcome variable. So in this case, based around articulation rate. Now you might be wondering, how exactly does rope range work? What is it using to calculate a rope? And there's actually quite good documentation from the package on this one. I'm just going to send this to the, if you scroll down a bit, all of it is based around Kushka 2018, but it says, okay, if you have this type of model, it's calculated like this. If you have logistic regression, it's calculated like this. And there's some defaults for different model types. This is something I wouldn't just use it without thinking about it. You would maybe want to read this paper, consider what's best practice for the model that you want to fit, and consider what other people are doing in the field of research that you do. Now, again, I don't have to use just a vector on the rope function. I can send a whole model to it. So this is going to be a really conservative one where I have a much bigger rope, and then I'm going to use the 0.95 confidence interval. When you send the whole model there, it'll tell you the percentage of the HDI within the rope, for all of the parameters that we've estimated. So in this case, for the intercept, as well as for attitude, polite, that condition. And in this case, none of the intercept is there. This makes perfect sense. We've already seen a few plots where it was actually really far away. The one before this, actually, so way out here. And then for the attitude, polite, we can see that some of it, why this isn't the plot there. Hang on. Let me give you the real plot. This is the real plot. We see the rope. We can see some of the posterior distribution for the attitude pull condition falls within the rope. How much of it? 5.6%. So that's what we see here in red. And in fact, I can zoom in on that. Let me take away the intercept so that we get closer and we can see that much more. So we're talking about this area right here. This is about 5% of the posterior falls within our region of practical equivalence. Okay, so this is a much more conservative approach. If we want to, we can also run this on a range of credible intervals at the same time. Let me move this so you can see it a bit better, right? We can just concatenate a vector of numbers together, right? And set that as our confidence interval. And then when we run this, it'll actually give us 3 different tables, right? Assuming that our HDI is 90%, a 90% credible interval, this is the percentage of the HDI that falls within the rope. Assuming that it's 95%, this is the amount. We can see that as we get a more conservative credible interval, the amount that is inside the rope increases, right? And then the most conservative 199, we can see 7% falls within the rope. And again, there are plotting methods for this. So I can just send this to here. And then they use different colors to represent the different credible intervals that are shown here, how much of them fall within the rope. Awesome. I can take a couple questions or go back to live coding or the slides.
Maybe we can, there's a question. It relates basically to the idea, like, so how do we use these ropes now to draw conclusions? So here's a question. If we have 5% of the data inside the rope, could that be evidence that we set the rope incorrectly? Could you discuss this with a practical example?
Yes. So you would want to set your rope a priori, which implies that you would have to do a lot of thinking here and think about what is a meaningful rope, what makes sense based on previous research and what have you. It is entirely possible to set a rope that is too conservative. But I would say that would be the burden of that is on the researcher. You have to think about what you're actually trying to fit here. Actually, see if I can read the question because I don't remember the rest of what you said.
Let me jump in maybe with a concrete example.
Right.
Articulation rate is probably not too intuitive. I have no, I personally don't have like an idea about what a rope would be. But for example, some of you know I worked on incomplete neutralization of final devoicing, right? A very minuscule effect of residual effect of voicing that we keep finding in experiments, even though German is described as having final devoicing, like a complete neutralization of the voicing contrast. Now we run these experiments over and over again, and we find effects. I mean, there are probably 5 people in the room that have worked on this topic. And we find sometimes effects of 2, 3 milliseconds, 4 milliseconds, 6 milliseconds of the vowel duration preceding the stop when we compare voiced, voiceless and devoiced stops. Right now, the question is obviously what we are after. Are we interested in whether there is a communicative difference between these two sets of words that have a devoiced or a voiceless stop? If we're interested in that, right, and any kind of communicative difference between them, then we probably have to relate somehow the values that we measure to stuff that we can actually hear reliably, right? Keyword, just noticeable difference, right? Obviously, that's a different concept, a difficult concept in its own, and it's not really entirely clear for different measurements where to set these just noticeable differences. But that would be psychophysics would be an area where we could define a rope theory-driven. We could define an area around 0 that we consider theoretically irrelevant. Right? For example, if you're interested in color perception, there's certain thresholds that cannot be perceived reliable by the human eye. And then we have that in speech as well. So in these scenarios, there might be theoretically motivated ways to define a rope, right? And we want if we really want to make a case for communicatively relevant phonetic difference, then we should relate our posterior to that rope that is theoretically derived from what we know about human communication and what we know about human perception. Right? This would be an example. And again, there's no rule of thumb how much of the posterior should not be in the rope or be in the rope to make any kind of conclusive calls. But at least we can relate it to something that we are theoretically motivating. So that is maybe an example that is a little bit more tangible for us.
I have another example that's related to some of the research that I do with bilinguals. A lot of time, for example, we work on voice onset time. That's something that's near and dear to most of our hearts. A lot of research on second language acquisition and bilingualism looks at voice onset time of voiceless stops, for example, and they try to make claims about, for example, bilinguals having different categories for monolinguals of the same language in their production of stops. And this would be an area where you setting up a rope would make a lot of sense, where you could say, okay, if we know that an aspirated stop, for example, has a range of around maybe 30 milliseconds to 60 milliseconds or somewhere in there, maybe bigger, depending on your distribution. Finding a difference between groups of 4 or 5 milliseconds probably doesn't mean a lot, depending on where it falls within the distribution. So this is even a case where you could set up a rope and it wouldn't even have to be around 0.0. You could establish where exactly you wanted it to be and what the range would make sense for. And it comes down to the same thing. At the end of the day, if what you want to say is there's a communicative difference in the way that a certain group is producing a stop, for example, then you have to think about what is perceptible, what makes sense, what is meaningful. And it always come back to the same question. And you could think of it, I'm not going to give another example, but you could also think of this relating it to pitch. I know a lot of people here work on intonation. You could think about what is a meaningful difference in a pitch difference, for example, stressed and unstressed syllables. Not okay, almost okay. All right, there we go. So we left off talking about ropes, regions of practical equivalence, and that was actually the end of the methods that I was going to show you, but I do want to briefly talk about some other methods. Some are pretty well established and some of them are being actively developed. I'm going to mention them mainly so that you are aware that they exist, and I'll give some links so that you can look up more information about them if that is something that you're interested in. The first one I'll talk about is you can just basically define your own hypothesis using the hypothesis function that is part of the BRMS package. This allows you, this is probably most related to the first method we talked about of just using a credible interval. This relates more to that, comparing your posterior distribution with a specific value, or there's flexibility. You can compare your posterior distribution to a range of values, but I would say it is most closely related to the first method that we talked about. Bayes factors are another method that are specifically used for decision making. Again, I'm not going to talk about these. They are rather controversial. I will say that. Another one that you can look up on Twitter and see people fight about. But I do link to a good tutorial and a primer on the topic if that's something that you have read about or you're interested in knowing more about. Support intervals are closely related to Bayes factors, so I'm kind of lumping those in together. Finally, I also wanted to mention equivalence testing, which allows one to see if an estimate and its uncertainty or confidence interval falls within the rope, not how much of it falls in the rope, but if the whole thing falls within the rope. And also practical significance, which is similar. It's conceptualized as a unidirectional equivalence test. So this is the type of thing that you would do if you wanted to say that certain groups, for example, performed similarly on a given task. To give a concrete example, one thing that I always see in second language acquisition literature is where they want to compare groups. They want them to be similar in terms of proficiency so that they can measure something else. And they will use, for example, an ANOVA and then a p-value greater than 0.05 to say, okay, the groups weren't different from each other, which obviously is not the correct usage of that. So using equivalence tests, for example, is a method for determining that groups are statistically equivalent. So to begin to summarize, we touched on some of the many ways in which one can use the posterior distribution for statistical inferences. The main focus has been on emphasizing different ways we can use these tools to quantify uncertainty and to help us in making inferences. We talked about credible intervals. We talked about the probability of direction or the maximum probability of effect. regions of practical equivalence in conjunction with credible intervals, specifically in HDI. And then I mentioned some other methods in passing that could be worthwhile to look up. Now, these provide a rich set of tools that we have at our disposal that contrasts with the sole p-value available under a frequentist NHST framework. Now, we will do one last coding section in which I'm going to give you some questions that you can work through using some of these tools that we just talked about. So I will go back to our studio. If you continue scrolling down on line 359, there's a section where it says your turn. And then I go through and explain to it. Actually, I will just explain this just in case. But I will also say, as a bit of a warning, the answers are right here in the document. I have them numbered as question 1, question 2, question 3, and the answer is right underneath the question. So if you actually want to do this without knowing the answer, that might not be ideal, but I don't know, maybe if you have self-discipline, you could not look at the answer. What the hard part is the interpretation anyway. So let's see. Let's take some of these tools and we'll use them to test different hypotheses. Specifically, let's fit a different model. We're going to look at articulation rate as a function of music student. This is a variable in the polite data set that is binary. It indicates whether or not a given participant was a student of music or not a student of music. So to simplify, we can use the same priors that we had before, or you could think about this and set up some different priors, but you have some sample code that will work for you, right? And then here's a model formula or model template that you need to fill in the blanks for. Fit the model, answer there. And then as you scroll down, there are some specific questions, right? Using a credible interval, for example, determine whether or not there is compelling evidence that the articulation rate between non-music students and music students is non-zero. What is the probability that the estimate of the difference between non-music students and music students, and that is in the output, it says music student, yes. What is the probability that the effect is negative? And then again, consider the non-music music student difference, but quantify your uncertainty using a rope. Use a range and a confidence interval width of your choice. You would think about how you would justify that, and then plot the result of that. And then I do give you down here below even further another hint. There's another function in the base test R package called describe posterior, which actually does all of the methods that I talked about for you in one function. So it's actually quite useful. I wanted to build up our intuition about each of those things separately. But if you want to, you can actually just use this single function and do everything in one fell swoop. So we will leave you at that for, I think we said 10 minutes. And
yeah, is it? Should we say 10 minutes then?
Would you rather say something different?
I don't know. So if you wanna, yeah. So if you wanna open the example, somebody's asking from the console in our studio, you write open_exercise 6, and that's gonna open the exercise. And Tim also pasted the function in the chat.
Maybe you can speak to how you would report the results in a published paper. Like, how would you describe this result, just like casually? And we will signpost, we will offer you some published examples at the end, papers that you can look up and look at how people actually report these kind of results. And
right. Yeah. I would preface that by saying I think the best way to do that would be to check published papers and kind of get a feel for how people do that. I specifically would probably use the describe posterior function. So let me just print that real quick. And then I would go through describing exactly what we see here. So if I were talking about a specific effect for a music student, I would say something to the effect of the posterior median or the posterior mean, whichever one you prefer to calculate, and I would report what the value is. I would give the credible interval, and then I would give a specific statement after that, where I interpret the credible interval by saying something like, in other words, we're 95%, or in this case, 99% certain that the parameter estimate, given our data, our assumptions about the prior assumptions and the generative model, falls within, and I would report what that specific range is. I would also say how I would talk about when I describe the model beforehand, I would talk about what the rope is and what we established as the rope. And then I would say how much of the credible interval fell within the rope, right? So just go through describing it piece by piece. And then I also describe probability of direction. My tendency is to give all three of those. And in my experience, that has been enough.
Maybe we can provide people as a resource for later on. We can provide people with examples, dummy examples of how to report the 3 different inferences that Joseph has presented here. Natasha is, oh, sorry, go ahead.
No, I think that's a really good idea. We could probably add that for next Monday for the 3rd day. Add some more.
Yeah, exactly. Natasha has a concrete question. Maybe we have some time for that. Can you run through the output table that's created by line 416?
Right. So yeah, that's the table I have up here.
Yeah. Explain what each value of music student yes means.
Yes. Okay. So the very first one, by default, the describe posterior function gives you the posterior median of that distribution for whatever parameter you're looking at. You can change this to the mean if you prefer, but by default, it just uses the median. So imagine we have the distribution, right? A nice little distribution. The median of that distribution is negative 0.45, right? The 99% credible interval is the credible interval that we established to describe that distribution. So in this case, it's giving us the 99% of the most dense values of that probability distribution. And this is the range for that. PD is probability of direction. So this is the second tool that we talked about. And it's saying in this case, there is a 99.78% probability or chance that this case that the value is negative, right? You have to look at what the sign is of the median to tell if it's telling you 99% chance that it's negative versus for the intercept, since it's a positive median, it would be a 100% chance that this value is positive. So it's giving us information about the direction of the effect. This is the rope that the model used to calculate. This I established here in the code for rope range. I said, let's use a rope of negative 0.1.5 and 0.1.5. This was completely arbitrary. I just put it in there to give an example. I did make it slightly more conservative on purpose. If you use the rope range function on this data, it'll give you one of about negative 0.11. So it's pretty close to that, but slightly more conservative. And then the next column tells you how much of your credible interval falls within your rope that you established, right? So in this case, the credible interval that I put was 99. As you can see, that is here. And that is also shown right here. And this is telling me how much of it is in that. So in this case, it's 0.92% of my rope that I established with a very, very wide confidence interval falls within that range. And then these are the R-hat and ESS convergence diagnostics that we're going to talk about later on today. We haven't touched on those yet in the workshop. And I believe that covers everything.
Yeah, great. I think that was super useful to go through this entire table again. It's a lot of information.
Yeah, absolutely.